So we'll just go over our unit summary, guys. So our test is this time next week, 168 hours in a week. So from now, we'll go for 60 minutes. We've got 44 marks. You can bring your calculator and bring your own paper handwritten notes. I don't think we need a formula sheet this time. Like, that's calculus. There's no differential calculus in this. And as far as unit circle goes, you can rely on your calculator for that. Okay. So content's very short chapter as well, isn't it? And we know like 5A we even covered a little bit last lesson. So really the new stuff is 5B, where we're talking about the area between functions. 5C, where we're looking at kinematics using integration techniques. And then 5D, just generic problem solving, okay? So integrating from a rate to a quantity. Using a rate function, area under the curve of a rate function gives you some quantities. So as far as skills checklists go, we've got find the area of segments on the Cartesian plane bound by functions and axes. Find the area between functions using integration techniques and technology. Solve problems of motion using integration techniques, and then integrate rate functions. Okay, and then revision resources. We've got plenty of practice tests, and then the review sets there as well. If you run out, no doubt I'll be able to find you something. So let's leap straight in. Our first question here, we have find the exact area between the function f of x equals e and g of x equals x squared. Now we have to read this carefully. So a question similar to this involving this type, I'm focused on this part, will pop up. Okay, f of x equals e. E by itself is a number. Okay, this is the function f of x equals e. Which is, what is e? 2.7. Now whenever you type it in your calculator, it'll go e, and then it'll say, now what do I put there? So when we're going to type that one in our calculator, to graph it in a sec, we're going to put in the number 1. Okay, it's just e to the power of 1. The function is e. Now if we graph this, alright, so here's my x-axis, here's my y-axis, e is 2.72. Alright, so if I have y equals 2.72, it's the equation of a horizontal line. Alright, that's going to be it there. F of x equals e. And g of x is a quadratic, it's x squared, and we're very familiar with how that parabola looks. Okay, so if we're going to find the exact area between these two functions, we first need to know, well, where do they meet? We need to know what are the boundaries over which I'm going to integrate. So where do these functions meet? And they're going to meet when x squared equals e, when the functions are equal to one another, which means x is the square root of e. Alright, so plus or minus, alright, because we're square rooting it, there's two solutions. This is obviously the negative root e, and this is the positive root e. And we can express it as root e, or we can express it as e to the power of a half. Either of those is perfectly fine. And so then this area, the area bound by these two functions, is going to be the integral from minus root e to positive root e of the top function, take away the bottom function. So my top function is e, and my bottom function is x squared. Okay, the top function, take away the bottom function. Okay, so this is the thing that I want to stress to you, is this step here, is when we integrate e, e is not a function, it's a number in this circumstance. It's not a function because it doesn't have an x, okay, it's a number. So it's not going to integrate to e to the power of x. Does anyone know, what's this going to integrate to? E times x, alright? I'll remind you, whenever we integrate a constant, the integral of k is kx. This is a constant, it's a number. So when we integrate e, we're going to have e times x. That's correct? Okay, and we know the integral of x squared is x to the 3 on top of 3, and our boundary is from minus root e to root e. Okay, now we're asked to solve this exactly, which means we do need to process the fundamental theorem of calculus manually here. So I'm going to substitute in my upper boundary. We'll have e root e take root e to the power of 3 on top of 3. So that's my upper boundary. Take away, and then I'll sub in my lower boundary. minus e root e, and then we've got minus root e to the power of 3 on top of 3. Now we're going to have some like terms here, so I'll really draw those out for you. I might just come over here quickly to say, if we have the square root of e, I said before, we can express that as e to the half if you want to. And so if we have the square root of e to the power of 3, well, that's e to the half to the power of 3, which is the same as e to the 3 on 2. So that's what it will collect to. All right, that's what that one's going to collect to. And this one over here, if I have e to the 1 times e to the half, that's also going to collect to e to the power of 3 on 2. Okay, same base, so we add the powers. 1 plus a half is 3 on 2. So we have e to the 3 on 2. This is going to be e to the 3 on 2 on top of 3. Okay, so that's our upper boundary. Then we have our lower boundary. Now I have take minus, so that's going to become positive, that term. And then here, over here, we have lots of negatives going on. So let me explain. Whenever we have a negative to an odd power, this term is going to remain negative, okay? So for instance, if you have minus 1 times minus 1, okay, that's times itself 2 times, that's going to be an even number. But when we have the third negative, it's going to end up negative. So minus root e times minus root e times minus root e, it maintains its negativity. So this term, when we evaluate it to the power of 3, it's going to be negative. We have negative negative, which becomes positive. And then we have this negative out here, which makes it negative in the end. Okay? So you can do that over a series of steps. I encourage you to just take it slowly to make sure that we're applying the negative properly. So it remains negative, negative and negative become positive, and then this negative distribute, which makes it negative in the end. So that's e to the 3 on 2 on top of 3. Okay, so now we're going to look along here and try and collect like terms. They all have the same power, so they're all like terms. Okay, all of them are in terms of e to the 3 on 2. Here we have minus a third of it. Here we have one lot of it plus another lot of it. So these two are going to collect. That's 2 lots of e to the 3 on 2. And we have take 1/3 of e to the 3 on 2, and then take another third of e to the 3 on 2. So we've got 2 lots of it, take away 2/3 of it. That's going to leave us with 4 on 3 e to the 3 on 2. Now, one simple way you can collect those, okay, using your calculator, is that all of them are e to the 3 on 2. So if I just go the number, 2, take a third, we're left with 4/3. Okay, so that's how we can get that coefficient. If you want me to draw this out a bit more and explain some of these later fraction operations to you, feel free to. I want to emphasize one thing here. Two things. Obviously, we spoke about the integral of e and ex. The other thing is that we find the area exactly. However, we can use our calculator to confirm that we're correct. All right? If we type this integral into our calculator, we will get 5.9 something. I did it before, okay? And if we type this number into our calculator, guess what we're going to get? 5.9. That's how we know we've got the right answer exactly. We can confirm it with our calculator. If there's an error, and you've got time, that's where you can go back and start to look at fixing it and so forth. Okay, so we can really use our calculator to say, here's what the integral should be. I evaluate it exactly. Here's my answer. Is that the correct answer? Does it match what the calculator tells me? But really, because it wants the area exactly, we need to perform the operation. Okay, so that's our first question. We'll move on to our second one, where we have got a kinematics question. Unless anyone wants to ask anything. Okay, so we have given a particle accelerates according to the following function, a of t. So we've got an a of t function, which is half t, take away 3, and it's in meters per second squared. Part A, find the velocity function. Velocity function is the integral of acceleration function. So it's going to be the integral of half t take away 3. And when we integrate that, we're going to get half t squared on 2. So we'll get half, now when I've written this out, I've written the wrong function. Let's put a 2 there instead of half. The integral function is 2t take 3, so let's change that a little bit, 2t take 3. It's just going to make it a little bit nicer. Okay, so now when we integrate it, we're going to get t squared take 3t plus c. Alright, plus c because we don't have boundaries on this integral. And we're going to find v of t exactly given the initial velocity is 2 meters per second. So that means when time is 0, the velocity is 2. So when we sub in 0, we get 2, so therefore the c value is 2, so therefore the velocity function is t squared take 3t plus 2. Okay, so all we're doing there, that's a skill we learned last unit, finding a function exactly, except it's implicit in the question. Find the velocity function given initial velocity 2 meters a second. So that's our answer to part A. Okay, part B says show that the particle is stationary when time is 1 and time is 2. Alright, so what this means is we need to show that the velocity is 0 when time is 1 and time is 2. So that's as simple as going, alright, well, if I put the number 1 into the velocity function, I'm going to have 1 take 3 plus 2, which is 0. Alright, this is a velocity of 0. If velocity is 0, it's not moving, it's stationary. And v of 2, when we sub 2 in, we're going to have 2 squared take 3 times 2 plus 2. So we'll have 4 take 6 plus 2, which is also 0. That's all you're required to do there. So show that the particle is stationary. Another way that it can be done is it's stationary when the velocity equals 0. Okay? This is the velocity function. When's the velocity equal to 0? And we can factorize and state the roots. Okay? However, we can't just write an answer because we're required to show that it's stationary at these points. Okay? So this is an appropriate way of showing it. Factorizing this and applying the null factor law is also an appropriate way of showing. Okay, part C. Find the total distance travelled over the first 3 seconds. So whenever we're talking about total distance, we want to know how much has it moved to the right, how much has it moved to the left. We could draw a motion diagram, but I think that will sort of complicate it a bit. We can make it much easier. Consider the graph of this function, our velocity function. It's t squared take 3t plus 2. It's going to look like this. And we know it's stationary here when time is 1 and when time is 2. Not to scale. All right, this diagram. So what we know then is the area from 0 to 1 of v of t. That's going to be how far it's moved to the right. I say how far it's moved to the right because it's above the x-axis. All right? Now, the integral from 0 to 2, and I'm going to have to do the negative integral because it's below the x-axis. Whenever we have a function below the x-axis and we want to know the area, again, we need the negative of it. Okay? And then we're going to integrate from 2 to 3 of v of t. Now, if we're adding all of these parts together, okay, integral from 0 to 1 plus the negative integral, the negative because that part is below the x-axis, plus from 2 to 3, it's going to give us the total distance, okay? This part, how far it's moved to the right, how far it's moved to the left, and then how far it's moved to the right. We're adding up all those areas together. Now, there's what about the difference between this calculation and this calculation? Okay. Does anyone want to volunteer an answer? What's the difference between this one and this one?
The second one's if the phone moved to the right.
Correct. Yeah, it's considering when it's moved to the right, as it's treating that as negative. Yep. So what does that mean in terms of the context of it? So it's moved this much to the right and then this much to the left. If we evaluate this integral, okay, if you type this in, it's going to treat this as a negative area. All right, and so what that means is you have this, take away this, and then plus this. This is the displacement, okay? Area under the curve, regardless of when it changes direction, that's displacement, all right? This one is distance because we're considering when does it change direction, how far does it move in the opposite direction. Okay, now we are asked for the total distance, which means we would need to perform each of these calculations. All right, now probably the fastest way to do it would be in graph mode in your calculator. If we sketch the function, which I encourage you to do when we have a kinematics question, sketching the velocity function, because that shows you where it's changing direction and so forth. So this is our velocity function. X squared, take 3x plus 2. All right, there's not much area underneath the curve. I've got a pretty standard V window. Okay, and we just go G solve integral, and we can go from 0 to 1. Okay, I've got this region from 0 to 1. I'm going to clear out my displacement. Okay, this is 0.83 recurring. This one from, that should say 1. Alright, because we're going from 0 to 1, and then from 1 to 2, and then from 2 to 3. So 0.83, integral from 2 to 3, so we're going to calculate it again. Integral 2 to 3. G solve, sorry, I'm mixing myself up here. Integral from 1 to 2. So if you evaluate the integral from 1 to 2, it tells you it's negative 0.166 recurring, which means negative becomes positive 0.166. Now we want this area to be positive anyway because we're concerned with the magnitude of it, the size of that. Has anyone got the last one?
It'd be the same.
From 2 to 3. The same, is it? 0.833. Yep. All right, and so we can add those together. We don't need to state it as a fraction, it's fine. We've got 0.8333 plus 0.1666 plus 0.8333. Anyway, we'll have 1.833. Excellent. Okay, so let's answer it as well, rather than just having the unit. Find the total distance travelled. Okay, so our acceleration is in meters per second squared, so our distance is in meters, our velocity is in meters per second. Okay, make sure we answer in terms of the context. All right, now 3 here, let's have a look at this one. I've actually sketched this on the back in preparation. This is highlighting the difference between area and values of definite integrals. And you'll see this kind of question pop up a bit in previous practice tests. Okay, so we've got the equation of a line. Okay, let's read it. Consider the diagram below. The area of each region is expressed in terms of A, B, C, D, E, and F. The functions intersect at x is 0, x is 2, and x is 5. Okay, so they're the numbers where it intersects. The equation of the line is defined as f of x, and the polynomial is g of x. All right, so the line f of x, the polynomial g of x. Evaluate the following definite integrals. So the first one says the integral from 0 to 2 of f of x with regards to x. In terms of A, B, C, D, E, and F, evaluate the following integrals. So, 0 to 2 of f of x. This is the part we're considering first. F of x, okay. F of x is the equation of the line. I want the area under the curve from 0 to 2 of the equation of the line, B. Okay? In terms of A, B, C, D, E, and F, the area is B. Okay. How about from 0 to 2 of g of x? Okay, this is the area under the polynomial function. From 0 to 2, it's going to be the area of A plus the area of B. All right, any questions? Stop me. Okay, so they start pretty easy, these ones. These are sort of one markers. So that's A, B, C. C, we've got the integral from 2 to 5 of g of x. Okay, so from 2 to 5. All right, so if we're just evaluating g of x, which is this function here, from 2 to 5. All right, I'm just going to rub out that line now so we can look at it. It's going to be areas C and F. They're going to be positive, but area E is going to be negative because it's below the x-axis. Unless we discriminate with these boundaries, we must treat that area as a negative because it's below the x-axis. So the answer is going to be positive C, take away E, plus F. All right, the area, the integral from 0 to 5 of this function, this part's positive. Now this skill pops up a lot in the first exercise in area 5A and 5B, where we learn about going below the x-axis. Okay, so that was C. Let's go to D. We've got the integral from 0 to 2 of g of x take away f of x. Okay, g of x take away f of x. So this is the area between the function g of x and f of x from 0 to 2. This region here, the answer is A. All right, and then last one, from 0 to 5 of f of x take away g of x. Okay, now I think the best way to think about this one, there's a couple of ways, but probably the best way to think about this one would be to break it up into a couple of regions. What we have is we have the integral from 0 to 2 of f of x take g of x. If this helps, you can do this, but you don't have to. Plus the integral from 2 to 5 of f of x take g of x. They're the regions of which we can break it up into, can't we? We've got intersects at 0, 2, and 5. So that makes sense to break those boundaries up. Now, we've actually already performed a very similar calculation to this one. Very similar, okay? However, the difference is we had g of x take f of x. Down here we have f of x take g of x. So one way we can manipulate that is that we could write it as the negative from 0 to 2 of g of x take f of x. Okay? If you distribute this negative, you would obtain that. And we know that this value is A. So the answer for the first part from 0 to 2 is negative A. Now I'll explain why that's the case. Okay, I'll try and make a faster argument for it. I think that's a really drawn out way of saying it. We're asked the area of this integral here, but we have, normally we would do the top function, take the bottom function in order to get positive area. But here, in this question, they're expressing g of x take away f of x. They've got it around the wrong way. And if we do that, then that section will be negative. Okay, any questions about that? All right, then we'll go from 2 to 5. So if I'm looking over this region, from 2 to 5 of f of x take g of x. F of x is the equation of the line, g of x is the curve, so it's just going to be d plus e. So that one's a fair bit easier because that's around the correct way. We're doing the top function take the bottom function, so they remain positive. If we have it around the wrong way, then the area component has to be negative. Now, all we're doing here is evaluating definite integrals. So, because they're definite integrals and they're not in terms of finding area of a region, then the negative and the positive matter. Okay. All right, so that's it. These will pop up in the practice test, and I'm happy to put another one up if you guys want to have a bit of a practice of that. Maybe I'll draw one up here in a sec if you'd like to have a go. Otherwise, let's dedicate our efforts to your study. That's really good. Yeah, for sure. Yep.